Hello, Chem 110. This video is about how to do calculations that take into account significant figures. And this assumes that you've completed the first exercise, which is figuring out how many significant figures different numbers have. So there are two sets of rules for calculations, depending what kind of calculation you're doing. So we'll start with the easier one, which is for multiplication. And it's also for division because if you think about it, division is multiplication by 1 over the number you're dividing by. So it's the same thing. And the rule for multiplication and division is that your answer has to have the same number of sig figs as the number in your calculation that has the smallest number of sig figs. So I'll finish writing that out so you can get it down. The number in your calculation that has the smallest number of sig figs. So for multiplication and division, it's all about the number of sig figs in the numbers you're putting into your calculation. So we're going to do an example together, and you can stop the video when I do the example. So our example, you can try it yourself, is a problem that you've had in Chem 111. So what is the energy of a photon with a frequency nu equal to 9.8 times 10 to the 12 hertz or per second? Okay, and given is that Planck's constant H is 6.626 times 10 to the minus 34 joule seconds. Okay, and so to do this problem, just as a reminder, you're going to use the equation E equals H nu. So this is a multiplication problem. You have two numbers, nu and H. And so what you should do is figure out how many significant figures are in each of these numbers. There's one number, here's the other number. And then your answer needs to have the same number as the smaller one, which not the smaller number, but which one has the smaller number of sig figs. All right, so if you want to go ahead and solve this, you can do it. Just a reminder that when you get to changing your answer, you need to round your answer to the correct number of sig figs. All right, so you can stop the video and do this, and then come back when you want to see my answer. Okay, so my answer is, well, I'll go ahead and first show the sig figs. So the frequency here has 2 sig figs, and Planck's constant, as I've written it here, has 4 sig figs. So if I compare these two numbers, that tells me the answer will have to have 2 sig figs because that's the smaller number of significant figures. And if you think about it philosophically, it just means your answer can't be more precise than the numbers you put into it. That's always our guiding principle. All right, so if I go ahead and do this calculation, putting in the numbers, so 6.626 times 10 to the minus 34 joule seconds times, just wrote the wrong number, 9.8 times 10 to the 12 per seconds. If you put that into your calculator, I got 6.493 times 10 to the minus 21 joules, and I'm not done. That's not my answer. My answer has to have 2 sig figs. And so this will be significant, and this one, that means I have to round looking at the digit to the right. The digit to the right is greater than 5, so I round up. So my final answer is 6.5 times 10 to the minus 21 joules. And that is my answer. Sometimes I think students feel like, this is the real answer, and then this is, sometimes I'll see students put, approximately equal. Don't do that, because it's not this is the answer. This is the real answer. Because really, you don't know beyond that 10th of a decimal point here what this number should be because of sig figs. So that's the answer. I want to add a note here. which is something to pay attention to. So the note is don't degrade your sig figs by using constants with fewer sig figs than other numbers in the problem. So in this case, the constant was Planck's constant, and I gave you Planck's constant with 4 sig figs, which is normally what I do with it. The number that's the quote-unquote measurement in the problem here is the frequency, 2 sig figs. So as an example here, what I'm saying is, example is, don't use, say, h equals 6 times 10 to the minus 34 joule seconds. That's 1 sig fig. If you used that, your answer would have to have 1 sig fig. So you would have wasted one of the 2 sig figs in your quote-unquote measurement. So when you are using constants, it's a great idea to go, one more significant figure than your measurement. And in this case, I just always use 4 sig figs for Planck's constant because it's rare that I would have a calculation with more than that. But what you don't want to do is make your answer have fewer sig figs than it could just because of your choice of constant. All right, so that is multiplication and division. So now we'll do addition and subtraction. This rule I find difficult to articulate, so I'll say something that may or may not make sense, and then we'll do an example. Addition and subtraction, the deal here is that the answer has its last sig digit, I'm going to use the word digit there, in the same place as the least precise number in the calculation. And precise means how far to the right does your number go. Okay, so that statement's true, but I think it's sort of hard to see. So we'll try an example. Okay, so here's an example, which really isn't chemistry, but I thought I'd do something different. So you have a bucket of rocks. There are 3 rocks, and their masses are 15 grams, 2.5 grams, and 12.76 grams. What is the total mass? So you can stop the video at any point and do this problem. Your answer has to have its last significant digit in the same place as the least precise number in the calculation. So one thing I want to emphasize right away is it's not about the total number of sig figs. I don't care that these numbers have 2, 2, and 4 sig figs. That's not what is relevant to addition and subtraction. What is relevant is the place. And so it's helpful to go through and just show where the last significant digit is. And which one of these is in the least precise place? Well, it's this one. This one is in the ones place. This one is in the tenths. This one's in the hundredths. And I think you can see that last number is the most precise. We know the mass of that rock, for what reason I don't know, to the hundredth of a decimal place. So that means your answer has to end here. It has to end in the ones place. All right, so if you're ready to stop, you can stop and do the answer and come back when you're ready to see it. So, and I'll just say one thing also, if you're back now, sometimes it's easier to see if you line these things up like this. So if I line up their places, it has to be, my answer has to have its last significant figure in the last column where every number contributes. And so that column is right here. All right. So if I add these numbers together, I get, so the sum, if I just put them in my calculator, I get 30.26 grams. I need to round it to here, so I need to look at this number. And so the answer is 30 grams, which is, sort of ambiguous and not so satisfying, although nobody writes 3.0 times 10 to the 1 grams. You could write it, I suppose, as 0.0 0.030 kilograms, and that clearly tells you you have 2 sig figs, but that's how you do this. And I would accept the first answer in this class because it is ambiguous. All right, I want to end with just one final note about sig figs, which is this, another note. And this note is that counting numbers are infinitely significant. And to make the point there, I'm going to just do another example. So if you had, example, if I gave you a bucket and I said you have 4 rocks in that bucket, and each one has mass of 12.76 grams, the total mass equals, well, it's, you might not write this all out quite this way because it's sort of obvious, but 4 rocks times 12.76 grams per rock. And the answer is 51.04 grams. And the answer should have 4 sig figs because this answer has 4, this answer has 4. This is infinitely significant. What I mean by that is it's not 1 sig fig, because I'm not sure if I give you a bucket with 4 rocks in it, I know I'm not sure that, like, well, it has somewhere between 2 and 3, or sorry, 3 and 5, now that I can count. That's not what I mean, right? So I can count 4, absolutely, and I can be sure there are 4 rocks. I don't think there's 4.1 rocks, there are 4 rocks. They're countable integer numbers. So that number is infinitely significant, meaning it doesn't affect the calculation at all. And so in this case, you go with the 4 sig figs. And interestingly, once countable numbers get big enough, like if I gave you a bucket and I said, oh, it has 581 rocks in it, if you count that, it's pretty likely if you count that twice, you'll get a slightly different number if you don't count super carefully. So there's a point at which countable numbers lose their infinite significance, but in general, you can assume they are infinitely significant.